Okay, so today we're going to talk about circles. So we're going to start our unit on circles. This is new material. However, it's something that will help you get ready for the ACT. There's always circles on the ACT, and I know you'll see these again in Algebra 2 and College Algebra, so I wanted to go ahead and show you about circles. So a circle is a set of all the points on a plane that are equidistant from a point called the center of the circle. So this red outside edge around this first circle here, all those points are the same distance from the center, which is point C right there in the middle. Okay, all those points are the same distance from that. So a chord, let me just get a highlighter. A chord is a segment that has endpoints that touch the outside edge of a circle. A diameter is a special chord. Its endpoints are on the edges of the circle, but it goes through the center. So a diameter is a special chord. So we know that half a diameter is a radius. So, and the radius is also the distance between the circle and the outside edge of the circle and the center. All right, when we have segments and lines that go through circles, there's two different lines we could have. We could have a secant line that goes in and out the circle. It touches the circle in two places. So this secant line right here touches the line into the circle's edge in two places. And we could have a tangent line that only touches the circle in one location. Okay? Just for some reference, to name a circle, we have a big circle right here with a point inside and then outside a capital letter. So this circle, this first circle at the top of the page was called circle C, so because the center of it is point C. So we have a circle with a point inside and then a capital letter for the center. All right, so what it wants us to do right now is to practice finding different segments and different parts of this circle. So let me get my pen. So y'all just follow along with me. First of all, the center of this circle is point K right here. So we call the center point K. Okay, the center is always a point. All right, now radius are going to be line segments. So one radius is from K to L right there, or K to I, I'm sorry. So that is segment KI. And there's some other radii. K to L is also a radius. So it's anything from the center to the outside edge of the circle. So KL, segment KL is also a radius, and also segment KJ. So those are all radii. All right, a chord, sorry, I'm trying to erase these. A chord is a segment that has endpoints on the edge of the circle. So one of them is actually H to I right here. So segment HI. Another one would be segment JL. And another one would actually be our diameter right here because it goes through the center, JI. So that helps me to answer problem D. The diameter is segment JI. So we just talked about a diameter is a special chord. All right, a secant line is a line that goes through a circle in two different places. So that would be this line right here. So that would be, we can call it a line or we can call it a segment. I'm going to call it segment GI because it touches the circle. It goes through the circle and touches it in two places. A tangent only touches the circle in one place, and it's be this line right here. So we'd call that segment GJ. And the point of tangency is the point on the outside of the circle where the tangent line touches it. So that would be right there, point J. So those are just some properties of circles. And now we're going to talk about some theorems about circles. So here's the first one. I believe this is in our notes. It says, in a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint. So if we have a line that's tangent to the circle, then it's going to be perpendicular to a radius. And it says if and only if, so that goes by both ways. That's biconditional. It goes both ways. So if you have a radius, it's going to be perpendicular to a tangent, and if you have a tangent, it's going to be perpendicular to a radius. So this is what you're going to have to do on your worksheet. So if you want to, after you do this problem, do a few problems on your worksheet. I know the first 4 problems is exactly what you're going to have to do. It says determine if or verify a tangent to the circle. So you're verifying whether ST is tangent to the circle. So it says PT, segment PT right here is a radius of that circle. So it tells me it's a radius. That means it tells me that P is the center. Is segment ST right there tangent to circle P? So I want to know if ST is a tangent line. Well, that theorem that I just talked about right there told me if it is tangent to it, then it's perpendicular to this radius. Well, what does it look like I've just drawn there? Well, it looks like I have drawn a right triangle. So if this is a right triangle, then that means the Pythagorean theorem would be true. Okay, so that means that the radius would be a leg, ST would be a leg, and SP right here would be the hypotenuse. Okay, so we're going to test out the Pythagorean theorem. If the Pythagorean theorem is true for this triangle, then it is tangent. So I'm going to test it out. Leg squared plus leg squared equals hypotenuse squared. So 12 squared is 144. I am using my calculator to help me. 35 squared is 1225. And 37 squared is 1369. And then I'm going to add those to verify. 144 plus 1225. That does equal 1369. So when it says, is segment ST tangent to circle P? Yes, because the Pythagorean theorem works. Since it's tangent, that means that that is perpendicular, which means that we'd have a right triangle. And if we have a right triangle, then the Pythagorean theorem should be true. So if you test the Pythagorean theorem to see if you have a right triangle. So if you do have a right triangle, then you know it's perpendicular and that it's tangent. So you're going to do basically Pythagorean theorem on all of 1 through 4 on your worksheet. So there's your little hint right there. Okay, now these are where there's complicated. So this is like the back or the second page of the worksheet, starting with number 9, I believe. Actually, starting with number 10. So this is where it gets more complicated. It says in the diagram, B is a point of tangency. So it tells me B is where segment AB is tangent to it. Find the radius of circle C. So we don't know what R is, okay? But we know that this is a leg. This is a leg. And this is the hypotenuse. That whole segment right there. So if it's tangent to it, that means the Pythagorean theorem will be true. Well, I don't know what R is. And that hypotenuse from here to here is 50 feet, but from here to here is R. So the hypotenuse is going to be R plus 50. So we're going to have to brush up on our Algebra 1 skills to be able to do this problem. And I'm going to show you why in a second. So I plug in my Pythagorean theorem, leg squared plus leg squared equals hypotenuse squared. So I've got R squared plus 80 squared equals parentheses R plus 50 squared. Now back in Algebra 1, I told you guys that R plus 50 squared is going to be R plus 50 times R plus 50. And I made a big deal saying that you don't distribute the square, and I told you that was bad math, and I did a murder scene on the board probably, and showed you how that was wrong. So you do not distribute the square when you square a binomial. You have to do the FOIL method. First, outer, inner, last. So let's remember that. So r times r is r squared. R times 50 is 50r. 50 times r, remember the rainbows, and then and then 50 times r is 50r, and then 50 times 50 is 2,500. Combine your middles, r squared plus 100r plus 2,500. So that's going to go over here, r squared plus 100r plus 2,500. Now I just got to finish the left side. R squared is going to stay r squared plus 80 squared is 6,400. Now watch what happens. I have an r squared on both sides, and if I get my r squareds together, they cancel. Uh-oh, I canceled out more than I meant to. And that did that too. What the heck? Okay, my computer likes to randomly delete things sometimes. I meant to eliminate, but not like that. So I'm canceling out my r squareds. So I have 6,400 equals 100r plus 2,500. And I'm solving for r, so I'm going to subtract 2,500 on both sides. That gets me 3,900 equals 100r, and then divide by 100, which means I can cancel out some zeros. So 39 equals r. So the radius, and you can check it with the Pythagorean theorem, 39 is going to equal the radius of that circle. So these are the most complicated ones that you're going to have to do when you just have r's for your radii or another variable, and you're going to have to come down here and do FOIL method. We have another example coming up later on if you need to see another one. All right. These are the easy ones. There's a few of these on your practice, not very many, but a couple. I think there's two. This is really easy. Tangent segments from a common external point are congruent. So SR is a segment that is tangent to circle P. TS is a tangent line to circle P. Now, since they both connect at point S, then that means those two lengths are congruent to each other. So SR is going to be congruent to ST. So let's see a problem. This just makes it so easy, y'all. It says RS is tangent to circle C and RT is tangent to circle C. So both of them have point R here. And that just deleted itself again. I don't understand what's happening. Find the value of X. Well, since they both have point R in them, that means that these two segments are congruent to each other. And if they're congruent to each other, we can set them equal to each other to solve for X. So 3x plus 4 equals 28. Subtract 4. 3x equals 24. Divide by 3, and x equals 8. Okay? And I can check it by plugging 8 into, for x, 3 times 8 is 24 plus 4 is 28. 28 on both sides. So if you have two tangent lines with a common external point, you just set those two lengths equal to each other to solve for the variable. Nothing too difficult. All right, this one is a U-try problem. It's also my last example for these notes. And this is one where you're going to have to do the Pythagorean theorem with the FOIL method. And the way I know I'm going to have to do that is because I have variables for my radii. Okay, so pause the video, try it on your own, and then unpause the video, and I'm going to work it out. Okay, so hopefully you've done this on your own. And so we're going to check it. So again, there's variables for the radii. So that lets me know I'm going to have to do it Pythagorean theorem, and then I'm also going to have to use FOIL method. So my legs are r and 24, and the hypotenuse is going to be r plus 18. That's the hypotenuse. So when I plug it into the Pythagorean theorem, leg squared plus leg squared equals hypotenuse squared. I have r squared plus 24 squared equals parentheses r plus 18 quantity squared. So I'm just going to copy this part, r squared plus 24 squared. Sorry, my calculator died. 24 squared is 576 equals, I'm going to come over here and do r plus 18 squared. So it's going to be r plus 18 times r plus 18. So, FOIL method, r times r is r squared, r times 18 is 18r. 18 times r is 18r, and 18 times 18 is 324. Combine your like terms. That is r squared plus 36r plus 324. So I put that over here for my hypotenuse. R squared plus 36r plus 324. Now, I have an r squared on each side, so if I subtract them on both sides, they cancel out. So now my equation just says 576 equals 36r plus 324. Solving for r. So I just need to subtract 324 on both sides. So 576 minus 324 is 252. And then I divide by 36. And I'm getting just 7. The radius is 7. And again, you could plug those into the Pythagorean theorem and check it. Your hypotenuse would be 7 plus 18, which would be 25. So 7 squared plus 24 squared should equal 25 squared. So that's how you do that. Those are a little bit long, but there's not very many of those on your worksheet. And if you need help, send me a message. Have a good day.